All right, welcome back. Okay, so in the last video, we were talking about probabilities and how the area underneath any curve that we make, any curve, any distribution, that area underneath the curve represents some probability, okay? And that cutoff point to where the shaded area stops makes up some kind of percentile, okay? It could be anything. And we know that the total area underneath a curve equals 1, okay? So we're going to kind of move on to another idea, and then at the very end, it's all going to start to make sense. I promise. I promise. So we have this idea of percentiles. We've talked about that. And then we have this idea of standardized scores. Okay. So if you've taken, let's see, what's the test to get into college? Oh yeah, the SAT. Gosh, it's been a while. So if you're taking the SAT or like the ACT, I guess that's the other one. That word shows up a lot, right? Those are standardized tests that kind of, well, the idea is that you're able to kind of absolutely see where everyone shows up based on their score that puts them in some kind of percentile, right? Okay. In statistics, we have the same idea. We have the same idea that we're able to compare a bunch of different groups. In this case, maybe scores on the SAT and the ACT, we're able to compare how well somebody did based on their standardized score. Okay, so this is also called a Z-score. I don't know why it's called Z. That's just, them's the rules, okay? But that is called a Z-score, where we standardize a bunch of different things, right? So we can do easier comparison between two groups or three groups or whatever. So let me draw out another example here that we're used to seeing. So let's say that we've got two towns, and they both have some town hall, and let me put their border towns. So maybe Pawnee and Eagleton, if you're familiar with Parks and Rec. Okay, so they both have town halls. And we are still using town hall sort of as our center. Okay, and let's say that Pawnee over here has got its town hall in its true center. All right, and Eagleton, on the other hand, it still bases everything around town hall, but it's not in the exact center. It's somewhere else in town. So we can still have the same amount. Let's see, we'll do this. We can still have the same amount of houses in each town. And now our question is, well, which town is more spread out? Which town, even though they look different, they have two different measures of center, right? The town halls are in two different locations. We're trying to figure out which town is more spread out, okay? We got to figure out a way to standardize these distances so we can have an easier time of comparing. Okay, now I'm not going to do this now, but this is the general idea with Z-scores. We're just going to kind of rescale everything to make the comparisons much easier. Okay, so Z-score is just a bit more a bit more information here. They're unit-free and they're standardized. Okay. And it just tells us how many standard deviations away something is from the mean. Okay, so that's the big thing here. That's the big thing, is that we're effectively measuring how far away something is in our good friend, standard deviations. Okay, and recall that a standard deviation essentially is just a measure of how far away something kind of deviates from a mean. Okay, so this Z-score here makes up, it comes from a distribution of a Z-distribution. But it turns out that a Z-distribution is just a fancy word for a normal distribution, okay? But a few caveats here, with the normal distribution. And I'll draw it out too. All right. So that's our x-axis. Our Z-distribution looks like this, okay? But our measure of center, our mean in a Z-distribution, is 0, okay, is 0. And then the standard deviation of our z-distribution is 1. So the average amount of deviation away from the mean is 1, all right? So we can even put that here. We can put that. I'll do it like this. So this would be -1. This would be 1, okay? And then we'll do it again. Over here, that might be 2. That might be -2, so on and so forth, right? Okay, so the mean of a z-distribution is 0. The standard deviation of a z-distribution is 1. It's bell-shaped, so, and it's also symmetric too. Let me write that. Same deal as the normal distribution. Okay, the tails never touch the x-axis. That's, you know, a detail that is true, but we'll never really have to deal anything with that. And then the whole area underneath the curve, just like we've seen before, equals 1, or represents 100% of the data. Okay, so we're going to be, oh yeah, gross. Okay, so we're going to be using this z-distribution all of the time. Okay, so we can have, if for instance we want to compare, well, let me take a step back. So let's say that we took the ACT and the SAT, and we're trying to figure out which one we did better on, right? We know that the ACT is on a scale from like, what, 0 to 38? No, more than that. Whatever. It doesn't really matter what the score is, but we know that the scaling is different than the SAT. The SAT is on a scale from like, gosh, 500 to 2400 or 36 or something, 3600. We know that those scales are much different, okay, but they both try to tell you the same thing, right? Well, whatever. You can have your own thoughts on what standardized tests do. I'm not a fan of them, but that's, again, beside the point. But they're both scaled differently, right? They're both scaled differently, and it's hard to say that, okay, maybe I got on the ACT, maybe I got a 32. Okay, I think that's pretty good. And then on the ACT, no, on the SAT, let's say that I got, I don't know, an 1800? I can't remember what the scores are. I should have looked this up before. But anyway, I don't know. I'm not really able to say, you know, absolutely how well I did because these scores look way different, right? Like a 32 is less than 1,800, but they both represent something different, right? Okay, so I'm trying to figure out the best way to compare these. Okay, so the general idea is then, well, what percentile do I fall in on both of these tests? And that will tell me maybe how well I did comparatively, right? So, or relatively. Okay, so that's the general idea. Now this gross looking thing, this gross looking thing is sometimes helpful, sometimes not. But it should be familiar once we sort of break it down a little bit. So this middle point here, this is the mean, right? The mean we see is 0. The actual score itself is 0. That's the data point that it represents. But everything below here makes up, check it out, 50% of the data. Everything above the mean makes up the other half. And all this is telling you is where sort of the percentile mark is for every standard deviation you go out. Okay, so one standard deviation away from 0 makes up 34% of the data, right? So this area right here makes up 34%. The other side makes up 34%. So this whole chunk right here, let me get this out of the way too, is just 0.3413 plus 0.3413, which that just turns out to be 68. Not actually, 0.68, right? Thereabout, okay? Or 68% of the data. And we can do this whole process for the other percentiles that we have here. Okay, so 34%, 34%, that is 68. It turns out that 2 standard deviations away on this end and this end make up 95% of the data. And you can kind of see where I'm going. The further you go out, the more you start to incorporate, the closer you get to 100%. Okay. Now there's a rule, there's a fun special rule with this that we'll go over at the end of this video. I guess at the end of this PowerPoint. But this is the general idea here. This is the general idea. Okay. So one last thing, just to kind of put it in your head, is that this makes up 1 standard deviation. Makes up 1 in both directions. Okay, so in both directions. So 1 standard deviation away from the mean, 1 SD. Let me draw like that too. 1 SD equals 68%. 2 standard deviations. All we need to do is add up all of these values up until the second standard deviation on both ends. That turns out to equal 95%, so on and so forth, right? So on and so forth. So we're sort of using this idea that we're using standard deviation as a true distance, So we're sort of measuring distance away from our mean value here of 0. Okay, this is probably not the easiest to comprehend. If it is easy for you, that's great. But if it's not, I promise, don't worry about it. Because when we start applying this idea, it will make much more sense. Okay, so let me see here. I'm going to pause the video again and go into an example. Okay, so I'll see you back.